CAP theorem, also called Brewer's theorem, is often cited when discussing availability guarantees for distributed systems or a system of compute interconnected by a network. It basically says that if you have, say, a database that runs on two or more computers, you can have linearizability, a specific consistency requirement, which I'll just say constrains what outputs are possible when an object is accessed by multiple processes concurrently, or availability, which means you can always get a response. You may have heard CAP theorem described as consistency, availability, or partition tolerance. Pick two. Oh, and by the way, you have to pick partition tolerance. Today on the podcast, we're speaking with Oren Eini, CEO of Hibernating Rhinos and creator of RavenDB. RavenDB is an open source NoSQL document database that is fully transactional. RavenDB includes a distributed database cluster, automatic indexing, easy-to-use GUI, top-of-the-line security, and in-memory performance for persistent database. Today, we're going to be discussing the backstory of RavenDB. We're going to discuss how Raven thinks about the CAP theorem. A spoiler alert, it thinks about it on two different levels. A bit about the choice of the implementation language, C#, and finally, index management with Raven. As always, thank you for joining me on your jogs, walks, and commutes. Oren, welcome to the podcast.
Thank you for having me.
So the very first question I have is right behind you on the screen. So the people that are listening can't see your screen, but it's Hibernating Rhinos, the name of the company behind RavenDB. Where does that come from?
It's a joke. It's an old joke. So around 2004, so 18 years ago, I got started in a Hibernate project, which is a port of the Hibernate ORM to .NET.
Yes.
And I was very heavily involved on that for a long time. I also was involved in several open source projects. And my tagline for most of those projects was Rhino something. Rhino mocks, Rhino service bus, Rhino distributed hash table, etc. So when I needed a name, I just smashed those things together and Hibernate Rhino came out, and it was hilariously funny to me at the time. And just to be clear, I'm living in Israel, which means that every time that I need to go to the store and buy a pen, and then they ask me, who do you want the invoice for? I have to tell them Hibernating Rhinos, and then I have to tell them how to spell that in Hebrew. So right now, I would have really wished I would call the company 123 or something like that, if only for that reason.
Yeah. Now you're going back to my early days. I came up as a Java developer, and then I transitioned into doing C# for some different companies and for some different roles that I was in. So I remember in Hibernate real well when I was trying to grasp for similar tools that I was kind of familiar with in the Java world to bring into the C#. So you definitely triggered some memories for me.
Trigger is the right word, I think.
Triggered, that's a good word, huh? Okay, so in the introduction, I mentioned that Raven is a fully transactional NoSQL document store. Go deeper into that. What's the problem that RavenDB is solving?
Go to 2006-07, thereabout. At the time, I was very big in the Hibernate community. I was going from customer to customer, building business applications and helping them meet their performance, reliability, all of the usual things that they want to have. And at the time, the most popular databases I worked with were SQL Server, MySQL, Oracle sometimes, stuff like that. And every single customer ran into problems. Now, I was working with Hibernate. I had a very deep level of knowledge about how to make Hibernate dance and do things. I was also a committer, so I could make change to the code base and have them there. And it felt like this never-ending journey of trying to make things work properly. At some point, I realized that the problem wasn't with the tooling that I had. The problem was the actual issue that I was trying to solve. Also, remember, at this time, domain-driven design was all the rage, and everyone wanted to build a proper model and domain for the system and build things properly. But there was this huge impedance mismatch between how you present your data in memory, story type objects, a lot of interconnection and complex things. And then you have to hydrate that to a database. And oh my God, you have 17 tables for a single object. And if you wanted to have a complex object graph with polymorphism and queries and things like that, well, you have a discriminator table, you have a union table, you have partial table inheritance. And also, we are in a podcast, but people, if you could see his face right now, he's like trigger all over the place. And the problem was you couldn't do that. The database that you used that actually fought you in order to do that. And you had options of either basically building transaction scripts And even if you want to build a transaction script, which is basically raw reads and write to the database, we are building such complex applications today, and 15, 20 years ago was the same in many respects, that the amount of back and forth that you had to go with the application database was huge. So I started looking into other options, and I ran into NoSQL databases at the time. And it was amazing because it broke an assumption in my head that the relational model is how you store data for persistence. So I started looking into all of those non-relational databases. And at the time, there were many of them. In 2007 or thereabout, there came the Dynamo paper from Amazon, which had a huge impact on the database scene. And there were all sorts of projects such as React and Project Voldemort, and a bunch of other stuff like that. MongoDB, CouchDB at the time, and all of them gave you a much better system to deal with a lot of those issues. However, if you actually looked into what you're giving up, it was horrendous. NoSQL databases typically did not have transactions, which is nice if you're building a system that can throw data away. MongoDB famously was meant to store logs. And okay, we lose one or two entry once in a while. No big deal. That wasn't the reason it was meant to be. So transactions are something that happened to somewhere else. But then you realize that, okay, I want to build a business application. I actually care about my data. I cannot accept no transactions. And some databases said, oh, you can get transactions if you write this horribly complicated dance in order to do that, which still isn't actually safe, but pretends to be so. So I started thinking I want to have a database that would be transaction, would give me all of the usual benefits that I get from a relational database, but also give me the proper modeling that I want.
What did that first MVP look like? So you set out with this goal. What came out?
So the first version was basically there is a storage engine that comes with Windows that is called eSent that was recently open sourced, recently as in 2-3 years ago. And this is a DLL that comes with every version of Windows that implements an ACID, B-tree, and ISAM index sequential access method. This is a very old terminology. I'm talking about the 70s, 60s even, but it is an amazing technology for many respects. And I took that as the ACID layer that I had. I plugged in Lucene for indexing, mixed them together with fairly primitive UI at that point, and I then created a client API that mimic to a large extent the API and Hibernate and other ORMs that give you the ability to operate on actual domain objects and persist them in a transactional manner with all of the usual things such as unit of work, chain tracking, all of those. And on top of that, you had a full text search, you had the ability to query the data in any arbitrary way, and the database would just respond to you.
So fast forward 15 years, 16 years from where that MVP release, when you look at the NoSQL landscape, it is definitely crowded, but there's also a lot of overlap. So where does RavenDB fit into the landscape next to things like Cassandra and MongoDB? And just in general, where does RavenDB excel and how does it differentiate itself?
RavenDB is a document database. It stores document in JSON format. In addition to JSON documents, you can also add additional data to a document. The data can be attachments, so some binary data of arbitrary size. And we like to think about it like attachments on an email, which turn up being a really useful feature. You can store distributed counters. This is very similar to the Cassandra feature, where you may have high throughput counter that is being modified in many nodes at the same time and converge to the right value. And again, this is a value that you can attach to a document. So a great example, if you have an Instagram post and you want to count the number of likes. So that's something very easy to do with this sort of feature. We also have revision support, so you can have automatic audit trail of all of the changes that happen to a document. And finally, we have the notion of time series, where you can attach a value that modify over time to a document. And the idea here, for example, I have a smartwatch, so my heart rate is being tracked over time, and I can add that to RavenDB. And The idea here is that each one of those 4 or 5 different aspects of a document have their own dedicated and optimized system that is meant to make it easy for you to implement all sorts of features. But going back to documents, a document is a JSON object that can be of arbitrary size. Practically speaking, RavenDB can accept a document up to about 2 gigabytes in size.
Okay.
Yeah, do not go that way. Other important features of RavenDB, you have a query language. We call it RQL, and just very similar to SQL, except that select is in the end, basically. You can also issue commands such as patches or transformations that happen on the server side. You can have a transaction that would modify multiple documents from the same collection, from different collection all at once. You have transactions that are either node local or cluster wide.
I want to switch over and talk about kind of a CAP theorem, consistent availability guarantee. A lot of times when we talk about databases, distributed systems, quickly CAP theorem comes up, right? And again, as I said in the intro, you can choose between consistency or linearizability, availability, and networking or network partitions. And oh, by the way, you always have to choose network partitions. So you can be AP, you can be CP. However, if you read the documentation about RavenDB, you kind of say, we're both. How is that possible?
The question is when? And we try to explain. A CAP theorem only applies when you have an actual failure. And that's important. So if you can be consistent and available as long as there is no failure in place. The problem is that you have to assume that at some point failures will happen. So the question is, how do I handle both the failure scenario and the success scenario? And it turns out that this is really hard to answer globally for all of your operations. So with RavenDB, you have 2 different levels that you can choose. There is the notion of a node local transaction, and there is the notion of a cluster-wide transaction. Now, cluster-wide transaction requires you to go through a majority of the nodes. And this is a standard distributed consensus system where we are consistent partition tolerance, and that's great for a certain set of operations that you have.
And specifically, that's Raft, right? When it comes to Raven, Raft is
Correct.
Okay.
Correct. By the way, it's funny, but I think that at this point there is Raft, Paxos, and View timestamp replication. And all of them, if you look deeply enough, are the same thing.
Just complexity is drastically different, right? And how Paxos versus Raft.
Oh, dear God. Oh, dear God. Just very small rant about Paxos. I have read all of the papers of Paxos. I went through all of the libpaxos implementation and a bunch of other implementations. I have written a Paxos implementation that works. I have sold that and used that commercially. And to this point, and I'm talking about 17 years of distributed programming experience, I have no sense of how this works.
Nice. You make the rest of us feel good about it too, then.
Yeah. And then I read the Raft paper, and it was like this show of angels singing. Like, I get it. There are details, and Raft isn't trivial to implement. Yeah, there are all sorts of pitfalls that you have to be aware of. But I grokked it. I understood the concept of how this is supposed to work. I could reason about it.
Yeah, you're not the first person to make that comment on the podcast to me.
Because that was what it was designed for, to be understandable. So we use Raft for distributed consensus, and that's good for high-value things. But the problem with distributed consensus that you have to apply that every single time. Now, in a cluster, that means that in order to accept a decision, you have to make at least 2 network round trips. If you're working on a transactional system, you have to pay the cost of multiple fsyncs to the disk, and that can dramatically increase the latency that you have. For the happy part, I'm not talking about the failure mode, just the happy part, you have a higher latency involved. Now, there are all ways of trying to reduce that and optimize, but in the end of the day, you have to do network round trips and fsyncs to the disk, and those things cost a lot. So RavenDB has this notion of node local transaction. And the idea here is that in many cases, you just want to store the data. And if there is a failure, we can recover afterward. In the case of RavenDB, there are 2 layers to the distributed nature of RavenDB. At the bottom layer, you have database nodes that are running using a gossip protocol, and a node local transaction would write the data to one of them and then asynchronously replicate it to the rest of the nodes in the cluster. At the Cluster level, you can have a cluster-wide transaction that would apply a transaction to all of the nodes in the cluster. So those are the two levels that you have.
One of the critiques of CAP theorem, I'm thinking specifically Martin Kleppman, his paper, I think 2015 or so, it's called a critique of the CAP theorem. And you referred to it a little while ago. It talks about like failure modes, like it's complete failure for network partition. But he kind of talks about things like slowness or just latency in the system. In this two-level design that you have, how does something like latency or slowness affect the different failure modes with RavenDB?
Depending on how you want to manage that. So let's talk about failure modes for a second. I write to RavenDB a set of documents, and I want them to be stored. By default, I would use a node local transaction, which means that I get to the node, it persisted to the disk.
So real quick, when you say a local node transaction, is that a specific operation that's doing that, or are you just writing to RavenDB that happens to be a local node operation?
So you have a transaction, you have a session, you modify things, then you call save changes. That batch, all of the changes that happen in the transaction is sent it to RavenDB in one shot. That batch of operations is going to be a transaction, and that's going to be persisted. You have the options of selecting that transaction to be a cluster-wide or node local transaction. And if this is a node local transaction, then that node will tell you, okay, I'm done. Once it flashed the data to disk, once it was made durable. And that's it. If you ask it to be a cluster-wide transaction, then it has to get a consensus that this has been persisted to disk on majority of the nodes in the cluster. So this is where you have the latency versus a consistency issue.
But just to that point, as the developer writing it, as the person interacting with it, you do have to be thinking about where you want this data persisted, cluster-wide or local. You need to make that.
No, in all cases, the data would be persisted cluster-wide. The issue is what is the consistency guarantees that you're requiring for that. And I know what is the value that is involved. So I can make that determination on a case-by-case basis.
I got it. So you're, as the person writing the code, executing the use case, or making the decision, like, what's my trade-off? But you're making that one, right? Got it. Okay.
Another thing that is important is that what happens if the node that I'm trying to write to has failed? Then RavenDB would transparently redirect the transaction to another node. So a node failure is just something that happens and you typically don't notice.
There's another question that I wanted to ask you about RavenDB. One of the things that kind of stood out to me as I was kind of diving in, looking into it, is the code base is in C#. What's the design thinking around C# as opposed to some of the other system languages that you might use today?
Say something like Rust.
I want to touch a little bit on Rust because it has a huge hype, and I wrote not insignificant amount of code in Rust. And I considered myself to be an okay developer, programmer, know quite a few languages, have enough experience to say that I've been around the block. And Rust is super annoying. You have to continuously make the compiler happy. Now, I spent a few weeks, 2 months, and separated by a couple of years trying to do things, and it just was really annoying to get things done. Conversely, in C, I swim because there is no mental overhead, and then I crash because of invalid memory exception or something like that. Here's the issue. Go into Rust and try to implement a binary tree or a tray or any interesting data structure which require you to modify memory. And you realize that this starts as impossible, and as you learn more, you become only slightly extremely hard. But that is specifically on Rust because I find it an ergonomic language. Going back to why C#.
Just real quick on that, though, like the Rust community would say, like the constructs like ownership within the language allow you to be able to do things like you're talking about more safely than in places like C++. So they'd argue that it's needed complexity.
Let me give you a great example. As a database, I deal with pages. I have a page that I get from the buffer manager, and this is a mutable page because I'm going to write to that. And I need to update the header, and I need to update the content of the page. The easiest way for me to manage that in C, for example, is to say, okay, let me cast the page pointer to the header and modify that. And let me cast the data portion of the page to a data objects array and manage that. And I try to do that with Rust. I know you cannot have mutable reference to the same thing, but that's what I actually want because I have this piece of memory that I arbitrarily decide that it needs to be muted in multiple ways. And the typical way you would resolve that in Rust would be, oh, just use a box or a RC or any of those sort of things. But in this case, I'm looking at the raw bytes that I'm working on. So you have to jump through multiple hops to do that. Or you have to copy the data, mutate it, and then copy it back, which is, I want to do a zero copy system. I actually had the challenge on doing a tray with Rust, where the challenge was here is 32 kilobyte of memory. This is the only thing that you're allowed to use. This is your buffer, and implement a threader. And people did it in Rust, which in a way that was completely unintuitive and broken.
Okay. All right. So C sharp. So don't like Rust.
Yeah. On the other hand, by the way, Zig is an amazing language. Really love it. Zig is very small. It competes with C and not C++, but it gives me all of the tools that I want to build system level software. It gets off my way and it's nice.
But you still have C sharp.
I still have C Sharp, yes. And I will explain why. C Sharp is an interesting language because go back to 2000 when it came out and realize that one of the things that made C Sharp distinct from Java was that Microsoft was blocked from adding extension to Java that made it work well on Windows. Things like being able to easily call to the Win32 APIs, being able to integrate well with COM object, those sort of things. And when Microsoft was forced to go with the .NET and the CLR, then they had a really interesting design. For example, you had value types from day one. You had the ability to allocate memory off the heap from day one because all of your existing infrastructure that you would integrate with require that. So calling to native code was trivial. That also meant that to a very large extent, the language was already geared to give you multiple levels in which you can work with. And I'm going back to C Sharp 1.0, but going back to C Sharp in 2015, at that time frame, we had reached a decision point for RavenDB. I built the architecture for RavenDB, the first three versions, where I knew not that much about databases, and we learned a lot in that time frame. And we couldn't push that architecture any longer. And we had all of the classic issues with managed systems. So high GC utilization, inability to control what's going on in many cases, stuff like that. And I sat down and wrote a design document for how we want to do things. And one of the things that were quite obvious to me is that I have to take ownership on all of the big resources that I have. So CPU, IO, and memory. And we looked into doing things in C++ or C at the time. And that was okay, let's start walking barefoot to Beijing, basically. I can do that. There is a lane path from here to Beijing, but that's probably not something that I want to do. And because, okay, where is my hash table? Or how do I do things like concurrent data structures? You can do that, but this is like this huge, complicated topic. So we looked into can we control the resources that we want in C Sharp? And it turns out that you can do that. You can allocate native memory, you can control your allocations. There are well-known patterns for object poolings, for off-heap allocations, for build your own thread pool. So you can have fine-grained control over where and how you're executing. And here is a great example. In RavenDB, which is a C-sharp application, we have our own string type. It's insane. I mean, the classic example about bad C++ code bases is that they have three different string types. Well, it turns out that for RavenDB, we deal a lot with JSON, obviously. And one of the interesting things about that is that we did a performance analysis of what's costing us in terms of CPU utilization. And it turns out that 45% of our time was spent in one method, write escaped string. Because wherever we wanted to write a string to the network or anywhere else, we would have to check if this JSON string had an escape character in it and then escaped it. And now we kind of write a lot of JSON strings. So what we did was, okay, reads and writes in RavenDB are typically skewed heavily toward reads. So when we read a document from the network, we store it internally in a format that tells us where the escape positions are. So in most cases, when I write it, I can just send the full block directly to the network without having to do any processing. And we also implemented our own JSON document type. And the reason for that was that I can now have a system that is zero copy. If you think about it, if you have a JSON string and you have, let's say, 100 kilobyte of a JSON string, I want you give me the name of the third person. You have two options. You can parse that into an in-memory object and then just process the DOM, or you can try to do a sequential scan and hope that you would find the result before the end, both of which are incredibly expensive. But there is another thing that you have to consider here. If you parse a JSON string into an object, you're at the mercy of the structure of that object. What do you mean by that? The cost of GC in all modern languages is based around the number of reachable objects that you have. But if you have a very complex JSON object, then as long as that has a reference, all of that object graph has a reference, and now you have to do far more work. So with RavenDB, a document is represented as a pointer to a mmap file, and we can just go directly into that. We can then traverse that document using pointer arithmetic to find the exact value that we want, and then send that over the network. And that's a difference of 1,800 times faster than the other alternative. The numbers are utterly insane, but it turns out that this is not sufficient because when you start to control your own memory, you start doing object pools and native memory and manage that yourself. Then you have all of this nice fast things that you have, but you'd also remove from the purview of the GC so much thing that it used to do. So now GC has a far smaller managed heap to work through, and you handle that. But, and this is funny because this is where it starts to get really interesting. I don't have to do that level of work each and every time. I can absolutely say, you know what? This is a debug endpoint. It happens once in 2 hours if someone is feeling generous. I can just write it in the fastest, quickest, generate some code, generate some memory, I don't care. Which means that my velocity for building things is far different. But there is also another thing here. In C++, in Rust, in Zig, any of the native languages, what happened if you messed up and you lost a reference to an object? Well, you have a memory leak. Enjoy finding that. Here's what happened with the way we did things. We have native memory, and if we lose a reference to that, the GC will come and clean up after me because I have a managed object that holds a handle to this native memory. And if I lost access to that, the GC would collect that. It would execute a finalizer. In debug, I would get this big notice, hey, something happened, you missed something, and I would go and fix that. But in production, that means that I have someone who is making sure that I'm still up and running, even if something happened.
So you like C Sharp, or you chose C Sharp because it gives you kind of a managed platform, a managed framework that lets you operate both at a lower system level and still operate quickly for times when you don't need that lower level programming to be able to improve velocity by working just at a higher level. So you can operate at two levels plus get a managed framework.
There is actually another interesting scenario that came up here. So the interesting thing about it is that we started very early and it was a rough journey. But along the way, something really interesting happened in the community because all of the things that we had to implement on our own, direct memory management, things like that, suddenly they're in the framework. We have span and memory right now, and there is a far greater awareness in the community, in the code base in general, for the hidden quirks that we have. For example, one of the things that we had to implement on our own was a stream reader. Now, there is a stream reader in the .NET framework, but I cannot use that. I cannot use that because whenever you create a new stream reader, it allocates two buffers, one that is 4 kilobyte in size and one that is 2 kilobyte in size. Why? Because that's the internal buffers that it needs to map between pages and characters. Well, that sucks for me if I have to create a lot of this. I had to create my own that avoided that. Now, this no longer happens. And the fact that .NET Core became open source and there is active encouragement of the community around that meant that a lot of the minor irritations got removed. If you look at the release notes, I think since 3.2.1 or something like that, of .NET, you can see that there is a huge number of community contributors. Each one of them removed this small, minor, annoying, here is an allocation, here is slightly better way of doing those sorts of things. And it turns out that this adds up a lot. We had a release where we just updated the .NET version that we're running. Performance cost dropped by 20%. So you can see that the isolated runtime was at 30% CPU most of the time, and then it dropped to 10% CPU, something like that.
All right, Oren, I need to start to wrap. It was an awesome conversation with you. I want to ask about what's next. I know that sharding is going to be re-added. It was removed a while back and it's being added again. So tell me about sharding and why it was removed in the first place.
So RavenDB force-gained sharding around 2011. And between 2015 and 2018, we had this big rewrite of everything, and sharding didn't make the cut. Or to be really more exact, we explicitly removed sharding from that. Now, sharding is a quite complicated topic. And because it became niche with the growth of hardware, we decided not to try to support it. But I want to explain something about how this works. Sharding support that we added in 2011 was from the client perspective. So you go and define the sharding configuration that you have on the client, and then the client would know how to route requests and things like that. That works and that's great. But what ended up happening over time is that we realized that we want to have as little configuration as possible on the client side. And the reason for that is how do you support operations? I want to be able to modify things, and I don't want to have to go and redeploy code to all of my clients. I want to be able to go to the database engine and say change and have it applied. So that was a real issue. So what we decided to do, we decided we want to implement sharding on the server side. And this is actually what we are busy doing for the 6.0 release of RavenDB, which we hope to be in mid Q3 of this year.
All right, Oren. Well, thank you for the conversation for today. Thank you for joining us, and I look forward to chatting with you again in the future.